Let's take a look at some new malware that's been shared by Cocoman on Malware Bazaar. So it has been received from this B3AC22D9F8 at email B box Pro. Now, this has been relayed through SendGrid, and it has an attachment that is an invoice. So we've got invoice bill, and it is an ISO file. Now, if we take a look at the TRID associated with this, we can see that it's picked up that 88.7% of this file is likely just null bytes, so isn't actually a part of the file itself. Now, I've got it downloaded, and if we open it up in a hexadecimal editor, we can actually see that the vast majority of these bytes are null bytes, just to kind of blow out the size of the file, I guess. If you've been around for a while, you'll know that there used to be something known as floppy disks, and shortly after that came something known as optical disks. Now, these optical disks, that's essentially what an ISO file is. It's the file that can be burnt to something like an optical disk, and it's the representation, the standardized format associated with that. On later versions of Windows, one of the features that Windows enabled was that you can mount ISO files natively by double-clicking on them. So if I double-click on this file, it will actually mount as a drive. So now this is the D drive that I have open here, and I'm no longer on my C drive. It's just mounted. Now if I double-click it again, it knows that it's already mounted, and it stays there as a DVD drive that's been opened. But to a user, maybe it'll look like a folder being opened, maybe it'll look like some sort of zip. Either way, the fact of the matter is these ISO formats have been used quite extensively to try and bypass security products actually picking up that they have malicious contents inside of them. Now, if I look at this, you'll notice that a.bat is actually a bit grayed out compared to this VBS script, and that's because it is a hidden item. It's been set to hide inside of this ISO. Now, if I disable viewing of that, we only see the VBS script. Now, this still doesn't make a lot of sense to me. It's not like they're trying to masquerade this as the actual invoice. I guess it obviously works so that they don't need to, and they've just said, yeah, I'm sure someone will double click on this and think that it's an invoice. This probably won't be that big, and if we go and edit it, you can actually see that all it's going to do is run a WScript shell that then kicks off a.bat. Now, a.bat is the other file that we have, so this is where we want to follow our analysis efforts. So let's take a look at this, but first I want to just highlight that now we've got this drive mounted. Even if we right click this and eject it, there is actually something that sits within the Windows event logs that can log that that mount has occurred. Now, I do have a one-liner on my website, and if you are interested in PowerShell one-liners and kind of digital forensics and incident response, check out this cheat sheet. I'm sure you'll find it useful. Let's take a look at what we can do though. I'm just going to run this, and I guess it says nothing meet my criteria, so that's actually a bad example. If we remove the fact that we were looking for that particular ID, I guess I'll update my website, and just look more broadly, we can actually see evidence of this ISO becoming surfaced as a disk, so VHD. So we have that ISO file that was sitting in our downloads directory, and we can see when it was both mounted and unmounted, so surfaced and unsurfaced. So now we have good timestamps associated when they mounted the ISO and when they unmounted the ISO. So let's go back and continue our analysis. Now we've got a.bat, and what does this actually kick off? Well, it looks like there's a bunch of stuff here that probably doesn't make a lot of sense to us, but then we get to the crux of what we need to look at. All of this probably isn't needed, but we can actually begin to make out some things in this script. And I'm going to open it up in Notepad++ just so that I can edit it a little bit easier. So all of this stuff immediately gets picked up as, hey, this is probably not relevant. It gets highlighted as such. What I'm going to do is I'm going to copy it out and then do some analysis. So we can copy this directly from the image file and just dump it on our desktop. So now I'm going to open this up. So now we've got a file that we actually can edit. Let's go ahead and delete the useless characters here. So now we can see that essentially what it's trying to do is replace any value that is defined as A with the letter E. So let's go ahead and do that. What we're going to do is we're just going to take that and we're going to replace that with the letter E. That's all we need to do. Now, there are some characters that are completely irrelevant. So the caret symbol, basically this one, if we replace that with null bytes, that's all we need to do. That is not going to be used anywhere throughout the actual script. So now we can actually see pretty much what's going to happen. It's going to spawn a PowerShell process, and this is going to be defining a byte array. and invoking in memory, and it's trying to download. So we have this tool here, and I'm sure that's being replaced somewhere. It is, so download string. Not a lot of obfuscation going on here, but it's pulling its next payload from this particular URL. Now, unfortunately, this is actually a legitimate website that's been compromised. You can see wp-admin, which is a clear indicator that this is a WordPress-based website, and the WordPress website has likely been compromised and has been used to serve some sort of malware. So this im.png, it's posing as a PNG file, but I doubt it's actually a PNG file. And if we actually try to scan this, there is something to keep in mind. If you try to scan it with a tool such as urlscan.io, because it's got a PNG extension, it will actually stop you from scanning it, but you can get around that by appending to the PNG extension. So you could put a question mark at the end, which is essentially a parameter, and that will allow you to still scan the PNG file. Now you'll notice that it doesn't look like a PNG file. We just have a broken image icon here because it's trying to interpret it as a PNG, but it isn't. Now, if we look at the response, we can actually see the next part of our payload. This is where we need to focus the next part of our analysis. Now, if I zoom into this, we can take this one step at a time. First off, it's defining a directory where it's going to likely be storing payloads. So this program data express. Now it takes a little bit of a rest, so it sleeps for 2 seconds, and then it starts to define its content. Now the content defines a couple of functions, so binary to string and hexa to byte. Now what we want to do is understand what is being passed to those functions. And if we scroll down, we can see a 45A. Now this is a good indication that this is going to be the MZ header associated with a PE file. So it does look like there are 2 PE files potentially under serve and data that are sitting ready to be invoked in memory. And if we go down further, you can see some pretty generic obfuscation, but let's take all of this so that we can perform some sort of data manipulation and understand what's going on. So I'm going to start a new file and paste all of this in. Now, first up, I want to understand what is happening here with this @ symbol. So it does look like when it is invoked, the hexa to byte on both serve and data, there is a replace operation that occurs on the @ symbol to replace it with the number 0. Pretty straightforward, which means if we take these and replace the value of @ with 0, then what it's going to be doing is converting them to their byte char equivalents. So that's where this base 16 comes in. And that's just going to give them the raw bytes that are going to be able to be used. So what I'm going to do is I'm going to take this and I'm going to throw it in CyberChef. So we have the first one in CyberChef. What I'm going to do is I'm just going to replace the @ symbol with a 0. Now we can see that it is identified as a Windows portable executable. So we have our next part of the payloads here. So I'm going to download it as, let's say, payload, or actually this was serve. So let's call this serve.exe, and we'll put that in our downloads. Then I'm going to also grab the next part, which is data, and data has the same operation occurred on it. We take that, we remove that, we have that, we do see it's a PE file, we save this as data. So now we have both serve and data.exe, and we want to do some more analysis on that. But first, let's just double check that there's nothing else happening in this script that's of interest. There is a definition of mxu and inv. Now, that seems to be the method and invoke, and what it's doing is it will replace these hashes with the number 0 or the hashes with the number 1, and then it will convert that from binary. So once again, let's throw this into CyberChef. We're going to do a simple replace that with 0, and that can be execute. So we know that that value is going to be execute. So we can actually just change this to the value execute. And now the invoke method, we're going to do the same thing, except replace it with the number 1. And so this is going to be invoke. It was not that obfuscated, but this is going to be something that we need when we get down to the bottom of this method here. Looking down, it does seem to be a little bit more that goes on. So let's just continue on while we've got this. We know that the hashes are really not doing anything in this script. So what we're going to do is just replace all of that with nothing. All right, so now we can actually begin to see something a bit more interesting. Let's remove the pluses as well. Let's replace that with nothing. And now we can see, all right, this is going to be using, it does look like this is meant to be wrapped. It's going to be using the Microsoft.NET Framework's ASP.NET compiler, and this is likely going to be used to inject into it, as this is specified as a path. So really what we want to do is understand what's happening in E3 here. And E3 is going to be the method defined by E2. E2 is going to be the type get.local, and that is going to be what is loaded from TXY, and this is going to be our data. So we have to understand what's happening in data now in order to progress. So I will note that this is using reflection and it's using load. So what that's telling me is that these are going to be .NET binaries, and these are going to be exposed methods that can be loaded in this kind of manner. Because of that, we can open it up in something like dnspy. So let's open it up. So I will point out that what is actually happening is that all of this is being defined in that content variable, and that content variable is going to be written to a file at that express cotrl.ps1, and then that is going to be invoked with PowerShell, but not before it kills the existing PowerShell process that starts running. So this task kill command is going to go off, kill PowerShell, and then it's going to run a different PowerShell script here. Something to be aware of. Then you can see that it does set a value of a batch file here. That is also going to be what is defined in the content variable, except this time the content variable gets overwritten. So really what is happening is it's setting all of this inside of this PS1 script, and then it's creating something with the same variable name. So it's replacing what was in that variable, and it's creating something that kicks off a PowerShell script after it kills the existing PowerShell processes. Then it's going to specify that this should be a batch script. So the batch script is going to launch the PowerShell script. Then we go down and we can see more content that is going to be written to a file. This time it's going to be a Visual Basic script that gets written to. And then after that, it looks like it's going to be doing the same, but creating persistence that then has a Visual Basic script that kicks off everything else. Ooh, bit of a mouthful. Anyway, let's take a look at the actual binaries that is then going to be loaded into memory. What we're going to do is we're going to open up dnspy. Let's zoom in a bit, maybe not that much. Let's go File, let's open it up. Let's take a look. We do have data, we have serve. Data is what I'm currently interested in. You can see Git, you can see reference to copyright 2022. Let's go and see what we can find. First off, we had the Git local that was specified, and it does look like this is fairly obfuscated. All right, maybe we need to do some deobfuscation of this. Let's see what we can deobfuscate first. So I'm just going to run a tool known as DE4 against those binaries. And this is a .NET deobfuscator. Let's see what we find. So we can see that it's detected it has used the confuser EX in order to make it a bit more difficult to understand. And I'm assuming that if we also have that on one binary, we're going to have that on the other. Except the other seems to be an unknown obfuscator. Interesting. Let's open back up dnspy and see what we find. I'm just going to go ahead and remove the previous binary that I added. And now I'm going to open up the new one. Now, if we expand this out and we begin to look at what it had, it does look like the local method has been deobfuscated slightly, so that's good for us. We can see that there is this method called execute, and this is really what we're interested in because we know that this is what's going to be loaded. It also has a path and a payload. So if we go back and we look at what we had, we know that this is going to be passing in some parameters. So that invoke, it's using the method that is execute and invoke. So we have execute. These are the parameters. That's to do with starting up the process. Over here are the two parameters that are going to be provided to that method. So path.replace. In this case, we know that path is the ASP.NET compiler. And then this variable, which we know is going to be the SRV payload. We have that payload, which is going to be injected into that ASP.NET compiler. And we know that injection is occurring because we can see API calls like ZW unmap view of section, read process memory, virtual AlecX, and write process memory, all of these which are associated with injection. Let's go ahead and open up the payload that's going to be injected into ASP.NET compiler. So we do have the serve cleaned, and serve is what we are actually looking for. We can see that this had instead a name that was DDD. So the other one is the loader. This is the payload. And what we want to do is understand when this is invoked, what is actually invoked within it. And there might not be a particular method that's going to be invoked. So we can go to the entry point of this binary, and that's going to be the main method that's going to be launched. So it does look like straight up it sleeps. There also seems to be these variables with a lot of environment.exit. So this is telling me that it will just terminate in a lot of situations, but let's see if we can find out why it will terminate. Let's see if we can find out more. Something from a base64 string, and the string is what's defined here, which is what's passed to this. Let's see if we can see any uses of this. So we can, there is one use by, which is this one, which means we have the string defined here, and it does look like there are a number of strings that are base64 encoded. And if they're just base64 encoded, there's probably not a lot to it. So let's go ahead and take all these strings that look to be base64 encoded. I'm actually just going to copy the whole lot because this doesn't look too large. I'm going to clear out my recipe and I'm just going to paste it in. Now I want to use some regex, and I also want to have the base64. From base64, I'm going to take this alphabet. I'm going to make that the regex. I'm going to say anything 30 or higher. And what I want it to do is just highlight at the moment, and it does look like it's picked up on a lot of the base64 encoded strings, if not all of it. So let's list the matches, and it does look like we have base64 here now, and let's say from base64. So it looks like there's probably something else that's happening here, because this has not given us any kind of plain text strings that then we can work with. So it's probably not as simple as just taking it and going from base64. So let's actually dive in and do some manual analysis, because dynamics is just a little bit too easy sometimes, and try to understand what this is doing. So for each and every one of these methods, because it does look like this is all probably some configuration of the malware, I want to understand what these are doing. It looks like there are the base64 encoded strings that we know have probably got some sort of encryption on them. So let's take a look at how we can implement AES decryption schemes in something like CyberChef. It's really not the nicest method of doing it, and you could probably do better by creating a Python script. But for the ease of demonstrating how we can actually implement these and understanding how AES encryption and decryption schemes are working in this malware, let's take a look at how it can be done in CyberChef. So first off, we have to understand what these strings are doing. This is getting a string from a base64 string. This base64 string is defined here as a static string. So we're going to need to take that because it's being used in the next function. The next function is deriving using RFC2898. Now, this is a password-based key derivation function. So PBKDF. And what this is doing is using a password, a salt, and a number of iterations, and a hashing scheme, deriving a secret password. If you don't have all these things in order, you're not going to get the password needed to be able to form the AES decryption. So what we're going to do is understand what's being passed here. We already have the master password, the master key, because this is stored in plaintext. This was the base64 encoded string. Then we have a salt. So this is being defined as this NYAT. And then we have a number of iterations. We have 50,000 iterations, and the salt is what's stored within these bytes. So what we're going to have to do is use these bytes. Let's jump over to CyberChef. What I've done is I've copied the bytes in, and they had a space, so I just did a find and replace to remove that. And then what I'm doing is converting it from decimal to something that is raw, and then from there I want it in a hexadecimal format as it's easy to work with. I could also do it as a base64 encoded format. So what I've actually got is an output that can be used. This output is the salt that's going to be used in our encryption scheme. Let's head back over to the malware though. So we first have to derive that key. We have to look at how it's being used in the AES decryption routine. And this seems to be in this ATPQ method. So if we head over here, it's going to convert from a base 64 string, then it's going to pass it through to this function. And what this is doing is taking it and performing the AES decryption on it. The key things that we want to know here is kind of the cipher mode, the padding scheme. Because it's got the PKCS7, this is going to work nicely. If it's not using this padding scheme, it can be a lot more challenging to actually do this in CyberChef. The key size is 256, which is what we're going to need to know. So let's head on over to CyberChef with this new knowledge. In CyberChef, we want to derive the key. Now we have the passphrase, this N3L, as this is what was passed to this function. The N3L is here. That's our passphrase. Now we need the key size. That's why we had to look at this new encryption routine in order to understand the key size that's being used. So in this case, it's 256. We have 50,000 iterations. That's because this has come from deriving the key with the 50,000 iterations. And it is the hashing function SHA-1. We didn't actually see that come up, but if you look at how RFC is defined here, it's using the hashing algorithm SHA-1. That's how we know that it's using SHA-1. And the salt is what we have derived from this. So that salt in bytes, when we convert that to hex, we can then easily use it in our PBKDF function. We now have this output, which seems to be this large hexadecimal value, and this is what we're going to need to use in our AES decryption. So let's jump over to how we can then take this and use it to decrypt these strings. What we want to do is actually have it as the key. We derived it. This is the key that we need. So let's use that as the key in the AES decryption function. There is also a initialization vector. Now, the initialization vector is going to be determined based on what you give it. And I'll show you how we find that out. If we look at the malware and we head on over to this decryption function, there is a mention here of a byte array that has 16 bytes in it. Now, this byte array is being used for the initialization vector. We can see that here in the AES crypto.iv. Now, those 16 bytes, they're being read from the memory stream. Now, the memory stream is what is being used to read in what we passed to this. And remember that this is all being passed the string to decrypt. So what this means is the initialization vector is actually the first 16 bytes of our encrypted string. So let's put this into practice. What I'm going to do is I'm going to take a string here. We've got this from base 64, but what I want to do is take those 16 bytes. So I'm going to run take bytes from 0 to 16. Now I also want this to be in hexadecimal, and I'm going to remove the space. So now we actually have something where we've taken the first 16 bytes, we've made it hexadecimal, and we've got an initialization vector. Let's disable these operations now and go back to the AES decrypt. If we put this in as IV, you immediately begin to see something interesting. The last value that shows up is false. So this looks like it's configuration details of some kind for the malware. What's even more interesting is that the IV value doesn't even really matter. As long as we've got 16 bytes in here, so even as hex, it still has the same output. The bytes preceding it are jumbled because I may have implemented this routine wrong, but the main thing that matters here is the false. So the configuration of this string is going to be false, and wherever it's used is going to be defined as false. I'm going to go back. So let's take all of these strings. I particularly want to know what this one is because it's quite large, and this one. There's quite a lot. So let's take them all besides what we know is going to be used, which is this N3 one. So let's take all of this. I'm going to throw this in the input. I'm going to get rid of the string, which is the master key. I'm going to get rid of some ones that are not related, like app data. What I want to do is extract this now with regex. We're going to use the same alphabet as defined in regex. We're going to say 30 or larger. This should pick up on every piece of base 64 encoded string here, and it does. Let's list the matches. So now it looks like we've got a whole list, which is nice. And one of the things that I want to do is now take this from base 64. But to do this properly, we're going to have to use a fork operation. We're going to split based on a new line, and then we're going to merge back at the end. Seems fine to me. Now I can do from base64, and everything should have the base64 operations occur. And then I can also continue with the AES decryption. And now we see things that look like configuration details. It may be that I need to actually drop some of the first lots of bytes. So let's go ahead and do that. Let's just drop, and I believe maybe it's the first 16, could be the first 32, 64. Let's just drop 32 for this point in time. It does look like perhaps this is communicating back on port 6666. There is the K helper. So it does look like it says edit 3losh rat. Now 3losh is a known crypter, so it's possible that that's been used on this rat. We can also see a mutex which is async mutex, and this is tied to AsyncRAT. So some of these strings don't seem to make a lot of sense. For example, we've got a few here. These other ones look like they might be, once again, base64 encoded strings though. So let's see if we can decode them. I'm going to take this one, I'm going to throw it over here. I'm going to say from base64, and you can actually see that this now says AsyncRAT server. Now this is a certificate file that's been detected here, so we have a good idea that this is a embedded certificate inside of the binary. And this is tied to AsyncRAT, which is commodity freely available rat. We can also see false, null, null, and a bat mentioned here. So it looks like we have now determined what this malware is. It's likely AsyncRAT. We can go and do some analysis on what AsyncRAT is. The code is freely available. So all in all, we know that this was a bit of a convoluted chain that pulled payloads from a compromised WordPress website, which was then going to invoke in memory a loader that then was going to be loading AsyncRAT into the ASP.NET compiler process. But that's all. That's what I wanted to show you today. Let me know your thoughts, feelings, comments, anything else in the comment section below, and I will catch you next time.